It's Nick from the University of Oxford. I'm now just going to start sharing my screen. I will keep my camera on such that you can see me waving my hands and pulling faces when stuff doesn't work. But if the audio starts not working very well, then I'll switch it off. So if you're starting to have problems with hearing me or seeing my slides, let me know and then I'll turn the camera off. Right. Cool. And I think Helen probably said, but I'm happy for you to kind of post questions throughout and we can decide whether we take the questions as I go or if we leave them to the end or whatever. I'll certainly leave time for questions. Right, so. Cool. Okay, so just bringing the last bits up. Cool. So, all right. As I said, good morning. My name is Nick. I'm from the Oxford Robotics Institute, and I've been running the remote inspection working group within RAIN. So this has been a group that's been pulling together, I think, research from a bunch of different angles within the consortium, and at a bunch of different technology readiness levels, so TRLs. So it's been an effort to combine some of the, I think, foundational or low TRL work on mobile autonomy, particularly that coming out of Oxford, but also some from Manchester and Bristol, with more specific nuclear sensing, the more mature technologies, perhaps coming out of Manchester, Lancaster, Bristol, for example, and then integrate those to provide demonstrator systems that we can use on nuclear inspection tasks with some of our end user partners. Whether that's RACE, UKRI, people like that. And so that's what we've been working on. And the point of this webinar today, so one of the reasons I left the camera on is that you can see me grimace when I say the word webinar. It's my least favorite word of the year so far. Is to kind of give everyone a sort of overview of what we've been doing for the last couple of years. So if you're a member of the RAIN consortium, then a lot of this will be old news to you. If you're from outside, then hopefully this is all new and exciting. I'm going to cover things at a reasonably high level, really just talk in broad strokes about what we've been doing, how we've been doing it, the technology we've been using. If you want more specific information about particular things, you can then either ask in the chat or drop me an email afterwards. My email's on the slide right now, or you can shout me on Twitter as well. And maybe actually there are certainly a bunch of people in the call who are able to answer some of the more technical questions more explicitly as well, which is great. Just looking through the list of people who are here. Excellent. Hello, everybody. Cool. So what have we been doing? Well, first of all, I guess it's useful for us to talk about what remote inspection is and how we've been considering it, because as I sort of hinted at the beginning, we've come from different backgrounds, and in particular, my background is academic. It's looking at AI techniques applied to robots, and industrial inspection was something that was relatively new to me at the start of RAIN. So we spent some time thinking about how we could kind of chop up the different bits of inspection and align it with some of the other things we knew about from different areas of technology. So for us, inspection has sort of two angles. There's the characterization element. So characterization is going into an environment and mapping it or measuring things for the first time. So we're trying to characterize it, so we don't know what's there. We're trying to measure things there. And then once we've done an initial characterization, then we're also interested in monitoring. So seeing how the measurements we take change. So characterization might be going into an environment, mapping the 3D space of that environment, and then also measuring, say, activity levels, gamma levels throughout the environment. And then monitoring will be going back to that environment and re-measuring those properties and seeing if there's any interesting changes occurring. We can go a bit further with characterization and say we might be interested in classification as well. So classification is then a kind of perceptual process that interprets the measurements we're taking. So we might try and classify different material types, different structures, the semantics of the environment, which is particularly important in areas where humans operate. and maybe grouping measurements or detecting important measurement values. In terms of monitoring, well, the key thing here that people are most interested in is typically change detection. So have my values changed from what they were previously, or have they changed in some unexpected way? So there's various things we might want to do in change detection, but these are the kind of space of things that we're interested in. And these kind of processes are carried out across a wide range of industries, nuclear and others. And in fact, in terms of autonomous systems, in terms of robots and autonomous robots, inspection is an absolute kind of leading use case of autonomous robotics. It's something, the reason for that, I mean, this is a different topic entirely. The reason for that is most inspection tasks in general can be carried out without any physical intervention. Of course, you typically want to do some intervention after you've done inspection. And for some cases, you need some physical interaction with the environment to do inspection in the first place. So if you want to take swabs, for example. But in general, we can do a lot of inspection without interacting physically with some element in the environment. And that makes the robotics angles much easier. So for those of you that are not robotics experts or familiar with robotics in general, the minute you start wanting your machine to physically or interact with the environment or apply forces to the environment, the problems multiply. So just being able to kind of point a sensor at some part of the environment to measure it is, an order of magnitude easier than trying to move or physically interact with the thing that you're looking at. And so yeah, that's one of the reasons for kind of focusing on inspection, particularly in this case where we're largely interested in working towards systems that have some kind of autonomy. So again, for those of you not in this field, we can think about robotics and autonomous robotics as somewhat separate. Robotics typically involves the construction of a physical device and the control of a physical device, where that control signal could come from a human remotely operating via a joystick or an interface, that robot platform. And then we can think about autonomy that's added to that system. So autonomy gives the system some degree of freedom to make choices for itself. That might be the choice of the target to inspect, the route to follow, the control torques to apply on particular joints. So autonomy gives the system some degree of self-control. And ultimately, we're interested in building platforms, or I'm interested certainly in building platforms that have that degree of autonomy, and that seems to be an interesting way to move the whole field of inspection. Of course, different bits of this process require different levels of autonomy and different input from humans. For example, classification, deciding if a particular value is interesting, is something that humans do much better than machines do. Okay, so this is the work presented from the kind of remote inspection working group. So typically we're thinking here about remote operation, where remote means distant from a human operator. So we want a system that is able, a robotic system that's able to perform some kind of inspection remote from that operator. And I've already sort of hinted at the two ways you might do this. You may have some teleoperation, so then you're kind of remote controlling that into the robot, and that remote control may come via joystick. It may come from kind of haptic control when you're moving a kind of sort of interacting with a master-slave device. Or remote operation can come through autonomous behavior, where you just instruct a robot to go off and inspect a particular environment. So the system would then have to choose much more about how it moves, where it points its sensors, etc. So remote operation for us encompasses both of these. We've certainly been doing more of our science towards the autonomy, at least in the mobile area, but within the RAIN consortium, there's a lot of work going on in teleoperation as well. So the other part that we can think about with remote operation, which is something we've not, at least within this presentation, the working group, we've not looked at very much, but is actually utterly essential to this remote inspection process, is how you get the data back from your remote system, how you visualize it, and how you use it to make decisions. So ultimately, all of this, all of these processes, all of these inspection processes are designed to help some user or some operator make better decisions, right? The inspection data is there to support some decision-making process, whether it's maintenance, safety, whatever. And so we may focus we will focus in this presentation about the robotic technology necessary to perform inspections, but ultimately you're really interested in the quality of your data and your ability to use that data to make decisions. So there's a kind of a later part of the pipeline where that becomes super important. That feeds into a lot of the ongoing discussions about digital twins or digital representations or duplicates of systems, which is one very natural way to think about modeling and using your data. And we'll mention a little bit about that towards the end of the presentation. Okay, so our inspection process, I mean, it's kind of useful. These are all different ways of thinking about the same problem. So you may find this is a little bit repetitive, but it's been useful for me to clarify the terminology that we use, and having kind of very sort of very vague flow diagrams like this is actually a very useful way of separating some of the key things we might think about. And in particular, I've been sort of trying to think about how we separate the work that, say, technology developers and scientists like us do, and how that interacts with existing users, existing maintainers of sites or platforms, for example. And I think there it's useful to think about the separation of a number of different areas of your remote inspection process or your remote inspection system. So we have the kind of physical hardware available to you. So that means what robotic platform you have, what sensors does that platform have. And often in robotics, that feels like a starting point. But in this context, really, it's sort of a midpoint. So you choose your platform and your sensors based on what the user wants to measure. So what environment you're going to work in, what your target measurements. Those are the kind of key things which will dictate your hardware platform and your sensors. The reason I say this is because and you'll see in the rest of this presentation, we've adopted a very narrow range of platforms, maybe a slightly wider range of sensors, because that's what we've had access to, and that's what we're able to use within kind of easily within a research context. But you shouldn't think of the physical platforms we're using as limiting the work in any way. What we've been doing is thinking about general research advancements we can make in the field of autonomy and inspection. And as is common for the kind of work we do, most of that can be ported to other hardware platforms, other sensor platforms. So this box here, when you see, this box up here, this platform and sensors box, in a robotics presentation, it often dominates the conversation. People see a particular robot and think, that is the robot that this person wants me to use for this task. And actually, that couldn't be further from the truth. In a lot of what we do, we're very neutral about the platforms we think are right, but we use the platforms that are best for us in terms of developing technology. Because ultimately, a lot of the technology we're thinking about is software-based, is control-based. So it's about the behavior of the system. And that's what this box is down here. This is another vague box, but ultimately you've got a robot, and you want that robot to support you in your inspection work. You have to work out how that robot should behave, particularly when we're talking about autonomous behavior, but equally under teleoperation. So the kind of box down here is something we're going to talk. We're going to talk mostly about this left-hand side, particularly how we process sensor data, what kind of sensors we've mounted onto existing platforms, and later on how we can change the behavior of these systems to deliver the kind of inspection schedules that we might be interested in, or inspection behavior we're interested in. As I said before, this generates data which can be used for visualizations and decisions, and then there's effectively some loop around here where the user wants to change their behavior, change the schedule of the inspections, for example, based on the results they've got to date. So this other arrow down diagonal that we didn't quite mention is really another part of the behavior we're interested in. How often, when should how often inspections should take place, when should they take place, and which areas of the environment should you inspect when, given the models you've got of, say, the degradation of that part of the environment. So that's another interesting part. I might pause here briefly and see if anyone's got any burning questions or burning clarifications that they require. Otherwise, I will just carry on. I can give you like 10 seconds to type in the chat.
So we've got one question. Are all your inspections visual inspection?
Okay, so we'll get onto this in a few slides' time. So we've used visual, we've used 3D information, so that's kind of laser or infrared, and we've also done gamma spectroscopy as well. So it's a range of inspection a range of sensors that are visual, structural, and sort of radiation focused. But I'll show you some videos and pictures of that later on. And I think this is one of these interesting things where if you've got a particular sensor that you think is important to your inspection process, then the interesting question is that how can you mount those kind of sensors on the robot, and how can you change the robot's behavior to use those sensors effectively? And this has been certainly a learning process from us from a robotics perspective, and that's where we've been working very closely with Lancaster, for example. Cool. And I see, so Steve's also posted that he's interested in the sensors and detectors we're using. And I think I saw Tilly Alton, who is in this call. So at some point, so she's been the person interacting with us most around sensors. So I might bring her in if the questions get a bit too technical for me on that front. Okay, right. So moving on, just to give you an overview of how we've been working before we get to the kind of what we've done part. So within the RAIN consortium, this has been an activity that started very broadly. So we had a meeting back in 2018 when we were allowed to leave the house and see other humans. There was unbelievably over 40 stakeholders, so industry. My VPN connection dropped. Yes. Can everyone still see me?
Yes, you froze for a minute, but you're back now.
Okay. So I'm connected to a VPN, which is necessary for the demo later. The VPN died, but I'll join that. I'll come back to that later. So if you see me trying to run the demo and failing, someone shout out, don't forget to connect back to the VPN. Okay. So yeah, we started with a group of kind of 40 plus industry representatives from kind of various tiers of suppliers to kind of people who own sites and the regulator and things like that. And we discussed a very broad range of inspection problems, particularly within the nuclear environment. We kind of drilled down from there to a smaller kind of focused group, bringing in a number of industry representatives and academic representatives across the consortium. And that was hugely valuable for us as a project because ultimately we're funded to develop technology to drive the future of industry in nuclear. So it's very important for us that we're solving problems that actually exist in industry. Equally, there's a slight tension there that we want to try and think beyond immediate needs and think about what kind of fundamental technologies will be required in the next decade or beyond that. And so there's a kind of a trade-off between thinking about what needs to be delivered immediately versus what we can start developing for the next, say, decade of robotics improvement. And that was something we tried to balance throughout the work we've done. So again, you might see demonstrations soon that are not things that solve problems that you have immediately, but our hope is they're general solutions that we'll show you that can be specialized to the kinds of things that you might be interested in. So that happened back in 2018. 2019, we kind of got more and more specialized. We came up with some concrete plans that I'll describe shortly. Then we integrated them or integrated software and hardware in a bunch of different places. So this started about a year ago, really, in kind of in earnest. And then we've kind of got more and more focused on a particular set of use cases over the last year. So that's the process. We started broad, we narrowed down until we were able to build and demonstrate some systems on real end user sites. So our idea was to develop a generic remote inspection platform. The idea here was to bring together a range of research being done in RAIN onto a single robot. This would give us a cross-RAIN demonstrator system that we could use and deploy and as a pathway for engagement. Here we're aiming for sort of capability, so the system should be able to do some useful things, not necessarily novelty. But of course, the aim is to do something that we can't do already. Otherwise, what's the point of us existing? And in particular, we were building a system, or bringing together, integrating a system to do inspection of objects and structures for radiation hotspots and structural change or structural degradation. And we've got a sort of a side interest in comparing off-the-shelf components, particularly detectors, with more research grade detectors as well. So we've been giving some thought as a group in how we're able to bring together and evaluate these different types of sensors and what we can use. So that was the general purpose. So in particular, I think this bit here is where we'll see most of the work going on for the rest of the presentation. So looking at inspection and monitoring objects and structures for radiation hotspots, but also kind of general background level radiation is something we're interested in, and at least taking measurements that will allow us to spot either visually or in 3D spatial changes or changes due to degradation. We've not done much work in terms of actually detecting those changes or that degradation yet. We've really been focused on gathering the data at this point. But again, that's something that the consortium is interested in the future. Okay, so as with all good things in engineering, we started this with lots of pizza. We got together as a group in Bristol about just over a year ago to start work here. And the focus here wasn't necessarily on the food, although that was highly important. It's important to show you where the taxpayers and industry money is going. But our main focus was on an initial integration of a set of components and a set of tools in order to build a sort of first pass integration system. So here you can see, and I'll go into a bit more detail in a minute, the first system we built. It's a mobile robot base, so we're using a ClearPath Husky, and you'll see this kind of the design of the mast replicated in a few different systems we see later. But the general idea is that we're going to mount on this mobile base a platform for inspection, so a pan tilt unit. So that's what this black box is here. So for those people who aren't roboticists, a pan tilt unit is a unit that can rotate and tilt. So that gives us the ability to point the sensors in a range of directions. We can also move the base of the robot in order to position our sensor differently. And we've been thinking about a number of different inspection sensors that we've been using. So something that allows us to do gamma spectroscopy. So I think here is a Chromac GR1 sensor, so an off-the-shelf sensor we've integrated. We've also used cerium bromide detectors from Lancaster. You can see here there's a very, very thin lead sheet wrapped around it for some collimation. So this was one of our early learning discoveries, that the kind of collimation we need to be effective to take directional readings for spectroscopy and activity measurements really do impact the performance of the robot's motion and the pan tilt unit. So our initial system, we didn't have a hardware platform up to the specs to carry the collimation we thought we needed, so we just got the bare minimum in there. Then we've got a LiDAR. So up here is a 2D planar LiDAR, so that gives us a nice two-dimensional sweep. It's mounted vertically so that we can sweep it side to side to get some 3D structure. And here we've just got a normal RGB camera, so we're also getting visual information. They're all put together on a 3D printed platform where we know the exact measurements, the exact focal positions of all these sensors, so we can then save us some calibration work later because we know roughly where those sensors are positioned in space. And that whole platform is then mounted on this Husky, and we're able to point it at structures in the environment. So here are two barrels, which may or may not contain radiation sources, and we can gather images and activity readings from those sources. So the aim here is to do everything in a way that is self-contained. So this is a similar system. You can see actually slightly, this is the next generation where we've got a slightly different set of printing here. This is, the aim is to have everything on board. So we've got two PCs, some NUCs, next unit of computation, sat inside the robot. We're carrying a bunch of networking, and you can see again the sensor mount. Here we've added a thermal camera. So, excuse me, for when we've been doing demonstrations of this system without radiation sources, we've been using thermal as a sort of placeholder for the radiation activities. And if any of you were at the Energous event last year, you'll have seen the demonstrations we've given with thermal sensing as well. So yeah, this was sort of the first version of the system. I think you can also get a sense of the complexity, the engineering complexity of building one of these kind of systems. So there's, in this image, there's wires everywhere, and this is because it's easier for us just to be able to plug things together and make it work while we're testing. But you'll see in later iterations of this, we can tighten things up a bit. Also, as well as what I didn't show you on the other screen is, as well as the kind of the inspection sensors, we have a bunch of autonomy sensors down here as well. So these down on the front of the robot are LiDARs, again, 2D LiDArs that allow us to localize the robot, so work out where it is in space. And then we'll have some kind of camera to give us a 3D view in front of the robot for obstacle avoidance. And we'll see these, again, these sensors change as we mature the platform. So this gives us a video of that first system running in Bristol. And this is useful because it gives us, even though the robot doesn't move, it gives us an idea of the kind of output we've been looking for. This was particularly the kind of output that was requested in that initial smaller working group where we asked industry what they wanted. And many people simply said, well, we want some model of the environment, some pictures of the environment, some 3D space, some 3D map, and we want heat maps over it. So we want to see where the activity levels are, so we can use it to detect hotspots and to monitor our environment. So this is the kind of thing that's typically done currently by humans with various forms of handheld detectors or gamma cameras, and the ability to automate that process, having a robot going to gather those measurements, has a number of advantages. Particularly in robotics, we gain the advantages of repeatability, so that we're able to go to particular locations with high accuracy at controlled times of day in order to gather that same degree of information every time. So the aim here is to be able to say, look, we can drive a platform up to some location in the environment and gather some sensing information, and then feed it back to the user in a 3D model with all the information attached. Of course, each one of these kind of colored dots on the screen is underpinned by a bunch of actual readings. So you could query any location in this video to get the list of readings that we got out. But this was an early system, and it taught us a lot about how to start thinking about the integration of gamma spectroscopy into this kind of 3D sensing. So from Oxford, our background is much more in this 3D sensing and autonomy. We're working here with Lancaster and Bristol in terms of integrating the sensor data from these kind of sensors. You can see it's sped up 20 times. And that's because we have to stay in one place for quite a long time with these sensors to get reliable readings, particularly the kind of distances we're talking about here. And so actually these kind of inspection problems turn into quite a slow process. That's another reason for having an automated system do it. If you want a wide range of readings, it's very hard for a human to stand there and take those. So having a robot perform this kind of inspection really gives you a bunch of advantages. So yeah, you can see this. The other thing we learned early on is that we can't just point a sensor. If you want to build some kind of heat map like this, you can't just point a sensor at the thing you're interested in, because you need some kind of reference points. You need to know the activity levels around it. So we started thinking a bit harder about how we scan the wider environment, how we measure background, how we integrate and visualize these bits of work. So that was kind of our first result from about a year ago. The other thing that was been working on in parallel, so this is some work from Tom Wright in Manchester, is that we wanted to start building ways of more naturally indicating the bits of the environment that the robot should inspect. So this is a tool that we developed, or that Thomas developed for actually taking a chunk of the environment, saying, look, these are the points or the 3D bits that you want the robot to look at. Because I'll show you in the next slide, we could be in an environment, say a drum store, where there are tons of things, hundreds of drums, hundreds of barrels for the robot to look at, and we don't really want to have the robot look at all of them. We typically want to indicate a subset the robot might be interested in. And ideally, we want to do this in 3 dimensions somehow. So, having the user select the points of space where you can do this. So this is one of the tools we've developed to do that. So we took our general system, the robot you saw before, and we've been working with UKRI down in Culham, and they've got a fantastic environment that they've been incredibly generous and let us have access to, which is their drum store. So this is a store for low-level waste. You can see the only kind of PPE you need or needed in this time is a high-vis jacket and a hard hat. There are potential for active barrels and interesting things happening in here, but it's a very, very well controlled site. But they still perform inspections regularly. There is incredibly low levels of activity here. But this has been incredibly useful for us as academics and researchers to have access to a site where we can start to go through some of the protocols and processes necessary to put an autonomous system, the kind of robot we saw previously, into a real functional nuclear site. And this has been one of the main advantages of the RAIN project. It's been giving us access and funding to be able to do these kinds of things. So this is a huge part of this general process of moving from lower TRL systems up to higher TRL. You have to have access to environments to kind of prove your technology. So here, what we've been doing is we've been, again, focused on drum inspection or barrel inspection. And we talked to the users there about the kinds of parts that they're interested in. So typically, we're interested in whether the drums or the barrels are deforming. We're interested in the integrity of the seams. So you can see down here, a seam where the barrel's been welded, and also the integrity of the kind of weld of the base. So those are just examples of the kind of things that we know are interesting to industry. We don't have the technology immediately to detect changes like that, but there is work going on in the project to both simulate those kind of changes and detect them autonomously. And actually, one of the big challenges there is having enough real data to build those detectors. So one of the things we've been doing, and I'll talk about a bit later on, is starting work to generate larger data sets of these kinds of images that we can use to systematically train AI systems to detect variations from normal storage conditions. This image also shows the kind of input we're looking for our overall system. So we typically go to an environment with our inspection team and scan it using a handheld scanner. There's some work going on in Oxford, led by Maurice Fallon, that can do this with a kind of backpack-based scanner on very large environments. In this example, we're using a Leica BLK, which is a kind of off-the-shelf commercial scanner, where you just go and you place the scanner in the middle of the room and build these 3D models. That gives you advantages, as kind of gives you a prior or a rough idea of the way the world appears initially, and we can use that to then map the environment to build the autonomous control for our robots, and gives us a sense of what's there. You can see a few things that are interesting in these images. So this is from this off-the-shelf scanner. What you can see is these black barrels typically don't appear in the final point cloud, so the final 3D map made by this commercial software. And that's because, of course, black is the absence of a reflection, and therefore the scanner is kind of interpreting that absence of a visual signal as absence of some physical structure. So it shows us that some off-the-shelf tools are not really doing the job that you'd want in these kind of environments, whereas the lasers we use pick up these black barrels fairly well. It's the latter processing, I think, in this case, that's throwing them away. Okay, so we've taken our system. So this is a kind of the next generation of the system that you saw in the previous slide, and ran some trials in real environments. So both in terms of the navigation autonomy and the scanning. So you can see here, the reason I've got this video in is we're running a bit faster. So there's only 4 times rather than 20 times. One of the reasons for that is now we've got stronger collimation. So we've got a custom designed collimator on the sensor. This is using a cerium bromide sensor, I think, which has been integrated into the system from Lancaster. So Tilly Alton of Lancaster has built a bunch of hardware and software for this integration. So in particular, we're running the output of that sensor into a Raspberry Pi, so not a Raspberry Pi, sorry, into an FPGA system that's sat on the robot, and then that FPGA system outputs into our ROS system, which is the robot operating system, which is what a lot of our systems are running. And that gives us kind of plug and play integration now of a range of different detectors that we can use. So the key trick here really was getting the right collimation and making sure we designed the pan tilt platform that we could have enough mobility on the sensor in order to build these kind of maps. And you can see actually we've got the thermal camera running here as well. Here we're not really sensing anything, we're just doing an overall scan. This gives us kind of a background map of activity. But in general, we're quite a long way away from many things, so it's not super accurate. And I can also show here's just some very kind of basic navigation autonomy. So what we had the robot do was drive around to specific locations that we had indicated in advance. So the robot's moving here, it's not being remote controlled, it's being indicated a target waypoint to visit. And we'll talk about that a lot more later on. But the robot here is performing autonomous navigation. You can see that by the very jerky turning. So we've got some tuning to do with the underlying control software to make the navigation a bit smoother. In general, with these kind of skid steer platforms, you don't really want them turning on the spot. It really shakes the robot around quite a lot. So that's not ideal, but again, it shows the value of using your systems in real environments to sort of test out that kind of behavior. So I think this is actually the precursor to the previous video. So the robot's now driving up to the inspection point that it's going to take. And this kind of autonomy, this kind of autonomous navigation is stuff we can do all day and all night with the tools we've got at Oxford, and in a whole range of environments. So here we're dealing in flat industrial settings, which is very natural for us, but we can use different platforms and different robots in different settings too. Yeah, so there's a robot driving up to a barrel. We can then see later on that the robot is going to do an inspection of this barrel. So I'll show you some images from that inspection next. So this is a real drum from the storage. There was efforts to find, from one of our colleagues there, Steve, the kind of liveliest drum that he thought he had in storage. And they placed this out for us. So of course, the livelier the barrel, the more likely we are to see something. But again, these are incredibly low levels of activity in these kinds of environments. So we're just using this as a proof of concept to check that we could see something. What you can see down here, the robot's up on stilts, because this, to get a kind of high accuracy readings, we let the robot run for a couple of hours. And we wanted to leave it on, so we left it unsupervised for a couple of hours. And just to be utterly safe, belt and braces and all, we didn't want to run the risk of it driving off. There was no way it could have done that. The motor stops were on, the navigation software wasn't running, but this just gives you that extra level of security. It's not necessary, but safety and verifiability of these systems is something that we're working on as well. So the team at Liverpool is looking at how you can guarantee safety of these kinds of autonomous systems, which is a key part of what we're doing. Okay, so here's some of the results, just a couple of images of this scan. We've not done any strong comparisons to ground truth. We're not really at that level of maturity yet, but this gives you an idea of the point cloud from the outside. So you can see particularly the laser on the robot was able to pick up a large amount of the structure from the tent, from the drum stall we were in. And again, we were able to, if we zoom in, look at the readings, you can see we actually localized the activity in the barrel quite accurately. So they knew there was something in the bottom of this barrel, and we can see that the activity there is higher than elsewhere. So from that, we've kind of demonstrated proof of concept here. There's lots of things in the system we'd like to change to make it more useful, but it gives us a rough idea that we can detect some interesting properties in the kind of environments we'd like. But for a kind of a one-off inspection, it's not clear to me the value of this. I think here we really want to start moving from these kind of one-off tests to longer-term inspections, because I think the decisions you can make with this kind of data become a lot more reliable when you have more data and you can understand how the system is sensing and operating in these kinds of environments. So that's the kind of what I'm going to move on now to talk about some different things and some future plans. So if anyone's got questions about this particular system, maybe now's the time to take them. I'm actually going to jump back 2 slides. We are also using some uncollimated sensors that's sitting on the robot down here that I didn't talk about, that we're using to measure kind of background levels. And the aim there is to move that towards measuring the kind of background levels as the robot moves and generating a larger kind of picture of the activity in this environment. So Guy asked, with the plan for to have the robot patrol the same route in the future? And I think absolutely that would be the idea. Maybe not the exact same route, but at least visit the same set of points over time. So some of that would be the same route, some of it would be different. But yeah, you can imagine the robot being a kind of patrol system, which has some kind of autonomous schedule that says, you're going to visit these locations every day, and provide the ability for users to then specify, okay, well, today I want an extra long scan of barrel 17.6. So I think we want to push towards a kind of long-term patrol behavior, which is something I'll talk about in a minute, but also it's important for the users to be able to override that kind of behavior with specific inspection tasks as well. And we'll show you a demo of how some of that might work fairly soon. I should speed up. Okay. So future plans for this, in particular, we're looking at a more challenging environment. So for us, our lives get increasingly interesting as the environments get increasingly realistic and the use cases get increasingly realistic. So we're now working with a larger team at UKRI and Race to place our Rain Husky into the hall outside the Jet Taurus. In particular, they've had a program for of taking measurements in this hall with a range of different detectors in order to kind of try to model the activity levels in the hall after the Taurus shuts down. And in order to detect kind of safe walking routes through the environment for human operators when they come in during shutdown. And so there's interest in detecting activities in these kinds of environments. And in particular, there's interest in detecting activity in a range of spatial locations over time in places that we can't necessarily position a sensor all the time, or we can't send a human into. So this is an ideal use case for the kind of technology we've got, where there's measurements we want, but we're not able to get them directly with a human or with fixed sensors. So over the last couple of months, we've been working on a new version of the system. And this is the grand reveal, in fact, of the kind of third generation Rain Husky. Now, this has been designed in conjunction with Health Physics, with UKRI, to make a system that is retrievable and decontaminatable. I guess that's a word. And that we've particularly been sort of avoiding problems due to the intake of dust into computers and things. So this is the kind of future version of the system. We've got increased collimation. We're putting additional sensing on it. We're going to carry additional 3D sensors. So this box on the front will give us a live or a 3D map using a tool from Oxford called Rooster from Maurice Fallon. And we're carrying tools, detectors from Lancaster on a larger PTU, on larger pan tilt unit. What you can see here is because we've increased collimation, we've moved to kind of we've gone to the next level up of kind of power of this unit, so we can carry a larger kind of more directed sensor. A large amount of this will then be wrapped in plastic from the materials fabrication facility at UKRI, so that we can kind of peel off some level of contamination and throw away things like the radiators. So this will be water cooled. At the back, you can see the kind of the cooling system, and we can throw away this and treat it as disposable, but we get to keep the majority of the robot. Maybe we throw away the wheels as well. But this will be going into highly active environments and being used to take measurements that the sensors team at Culham can compare to readings they've had previously in this environment. And we're hoping to contribute towards the long-term activity of measuring activities in this environment. So this is our kind of future plan with this system. So we found a kind of real concrete use case, and it's really helping us to push through an understanding of working in much more hazardous environments with full involvement of health physics and the whole wealth of engineering that we need to get these systems in. We're hoping, I think, to get a demonstration of this system done maybe towards the end of the year. We've been, of course, a bit knocked by COVID and a few other things, but we're hoping to get that in there. So that's the future of the Husky system. We've also been taking the same sort of technology and applying it in other application domains. So in particular, we're very interested in outdoor inspection, long-term outdoor inspection, and looking at solar. So we've been taking our inspection Husky with a slightly different sensor payload and looking at how we can inspect solar panels. This has some similarities and a number of dissimilarities. The key message here is that inspection with robots has a whole bunch of core technology that can be applied across sectors. And the work we're doing whilst driving forward in nuclear, the inspection work out of RAIN can be applied across application sectors. And again, you might need to change the physical platform or the sensors, but the underlying autonomy technology, localization, sensor processing, can be relatively portable. So some other work that's been funded initially by RAIN and has now been moved over to Innovate UK is work done out of Oxford by Maurice and Yanis. They're the Dynamic Robot Systems Group. So they've been, this was a collaboration pump primed by expansion funds out of RAIN with Createch to integrate their Envisage gamma detector, Envisage Recon, taking some of the components of this. So this is a handheld gamma camera that humans walk around pointing at things. We've been looking at integrating those, or these guys have been looking at integrating those into autonomous platforms or teleoperated platforms coming out of Oxford. So here we can see the animal, so a quadruped, which is useful for doing inspection in environments where you don't have the same degree of flat structure. So if you're looking at going through an environment maybe where you don't know what's in there, you don't want to get stuck on a ladder or a bump, you need to use something maybe with legs. So legged platforms are looking increasingly interesting in these settings. And here they've been working on, for example, how you can integrate the sensor. You can see the detector spinning on the top, but also you can see that the action of the robot has to change in order to point the sensor. And we can see down here, although it's now driven off screen, integration onto a jackal. So this is a smaller mobile robot that gives us the capability of doing longer term, more mobile inspections. And here the detector's sitting on top. So here's some future work that we hope to see driving into the commercial domain fairly soon. So I mentioned long term, and Guy Burrow's question kind of headed in this direction. How do we move from kind of one-off inspections to long-term inspection, to kind of persistent monitoring? So in that opening slides, I talked about characterization, which is what most of the things you've seen previously in this presentation were about. And I talked about monitoring, so change detection and data gathering over long periods of time. And that's where we're trying to transition to for the next stage of work within RAIN. How do we gather information over long periods of time in dynamic environments, where that information is both on the structure and the activity? Yes, and so we're looking, I'm just going to speed through this bit so we can get to the demo on time. We're looking at how we can deploy systems into these kinds of environments. And here we're looking again at using probably smaller robots, and we may be looking only at background information and 3D or visual structure. And so we're looking at how the changes in these environments change every day. Just to point you at a couple of things we're doing at the moment. Manchester are building some simulators we can use, because one of the challenges of doing long-term studies is that you can't, well, you impinge on people's goodwill if you try and deploy robots into their facilities for a long period of time. So Manchester have been building a fairly physically realistic simulators of both radioactivity and physical structure. So you can see a facility here modeled with the detected radiation levels visualized on the right. Tom Wright from Manchester as well has been looking at how we plan the use of barrels. And this is really where I think the next interesting set of work comes. Now we can start to take a scan, so a 2D scan of the environment. You can see the barrels all appear here correctly, and determine the locations for which we want to view these drums and send the robots to these locations repeatedly. So this is kind of the input to a longer term inspection process where we're going to drive mobile robots around like this in order to take these kinds of inspections. And in particular, we're very interested in mission planning. So how we can plan the sequence of inspections to take in a way that maximizes the return of information whilst minimizing the risk to the robot. And if a few of you might have seen us present this demo in the past, we're able to plan in a multi-objective way the value of information to the robot versus the risk it takes, for example, by exposure to radioactive sources. And to do this, you need a model in the environment, you need to be able to predict where the sources are, but you can then run these long-term inspection missions without the risk of damaging your robot in a particular environment. And if I had more time, I would go into that in a bit more detail. But I think that's something that if you're interested, please shout about how we do this kind of mission planning in risk-aware environments. And I think increasingly, when we think about autonomy, we have to take into account the risk to the system, the risk to the facility, the risk to the users in its use. And we want our robots to be able to plan with those kinds of things explicitly. And that's what we're seeing here. Okay, so at this point, I'm going to jump forward a bit and say a few remarks before going to a demonstration. A lot of the autonomy mission planning work we've been doing in RAIN has been built on top of some work we did in the European project previously called Strands, which worked on indoor autonomy. This work was joint with a number of partners, including the University of Lincoln, a colleague and friend there, Mark Hanheider. And as part of that, we developed for this kind of long-term, these were long-term deployments. The robots existed in these environments for weeks and months at a time, and we needed a way of remote operating them. So within this project, we developed a web-based interface to allow us to see what the robot was seeing and control it and visualize its tasks. And we've been working recently as part of an initiative that goes across the UKRI Robots for a Safer World hubs on something called the digital tissue, which has been looking at how we build remote tools for operation of robots and how we feed the data from robots into digital twins. And this work from Strands, these web-controlled interfaces have really featured heavily there. So we've been looking at actually how we integrate an extension of that web-based interface created by Lincoln for their agriculture projects into the kind of remote operation that we're interested in RAIN. So the video you see here is an overview of a web interface that's being used to control robots across a range of agriculture sites. But what I'm going to show you now is how we've adapted that to a particular operation setting for a jackal, which will then feed into inspection. So I am going to stop the slides there. I'm going to stop sharing my screen. I am going to rejoin. I've got a dog clawing my leg. Hello, okay. I'm going to rejoin the VPN, and I'm going to ask Michał, who's in a lab in Oxford, to turn his camera on. I've got rid of the dog now. I'm going to turn off my video, and I'm going to jump into a demo. Oops, right. Okay, so the weird noise you can hear right now is my mum's dog, who has just appeared in my house. It was desperate for some attention. I think I may have got rid of it. Okay, and I'm going to share my screen. Right, so I'm going to ask you now to do two things. First of all, I've turned my camera off, but if you look in the participants, you should see a person called Michał Staniszek, and he's got his camera on. And if you look at him, you should currently see in fact, I'm going to stop sharing my screen for now. So that's not visible. If you look at Michał, I'm going to ask, Michał's pointing his camera into a lab in Oxford. Michał, if you could just move your camera around to give us a slow tour of the environment we're in. What we'll see in Michał's environment, this is it's our new robotics lab in the ORI, in the Oxford Robotics Institute. So this is underground. It's currently about 10 miles from where I am. And it's a place we're using as a base for some remote operation experiments. You can see it's a fairly standard lab environment. And within this environment, there is a jackal robot. So now, thank you, Michał. I'm going to jump back to sharing my screen. But if you keep an eye on Michał, you will also see the robot moving shortly. So I've gone back to sharing my screen, and what we can see here is a remote operation interface that we can use for a robot. So we're using one of the jackals. So the jackal is now visible in Michał's screen. And you can see on this website a map that gives us an overview of the lab. So this is a lab built by the robot previously. And we also have a bunch of control commands. So we've got some simple teleoperation commands. So I can click here. If I click the right button, what you'll see is the camera changes because the robot is rotating. You should also see in Michał's camera the jackal robot rotating slightly to the right. And on here, we've got a bunch of waypoints. So you can think about these waypoints, these blue dots, as locations the robot can visit. Particularly, they could be the ways of viewing barrels. And at the bottom here, I have a bunch of tasks that I can send the robot. So I could ask the robot to visit the big door. So here we have the names of the waypoints and possible tasks. If I hit execute here, what we'll see is up here, the robot starts moving. This is the robot on the map moving towards big door. This is the big door in the screen up here. And the robot will then perform, which did I select? I selected just visit. So the robot is just going there. I can also ask the robot to perform an inspection mission. So rather than doing visit, I could say execute inspection. And for us, an inspection mission in this case is just a spin on the spot. So you'll see in a minute the robot turns in front of the doorway, and you'll get a kind of panoramic view of the robotic lab. You'll see it moving on the map. So and there's Michał. So what you can see here is the idea of how we might perform remote operations in a kind of inspection environment, the kind of operator interface that would at least the kind of baseline technology you need to embed one of these robots for long-term operation. The key thing here is it's remote as well. So I'm operating the robot, but I'm in a different bit of Oxford. So yeah, so 10 miles or so away from the robot. But what I've shown you so far is just the ability to do one task. What we're really interested is in mission planning. So I could select a bunch of targets, so office door and workshop, for example. And I could jump down here and say, well, I want you to visit office door. I'll unclick this one. And I want you to, sorry, no, what did I say? Workshop and yeah, office door. And maybe perform one task in each of those. If I hit execute tasks, you'll see now that the robot has a bunch of tasks that it knows it's performing. It knows what it's trying to currently do. And we can see it setting off navigating through the environment. So this is autonomous behavior. So rather than me remote controlling the robot and driving it to exactly where we want it to be, I've set the robot a set of goals. So I've given it a mission specification, which are the locations we want the robot to visit. And oops. So at the moment, I say that the environment has changed a little bit since we mapped it. So the navigation may not be perfect, but I'm sure it will find a way. I can always cancel it and try it again. But we're giving it a mission specification. So we've told it what we want it to do. We've not told it how it should do it. And the robot is computing for itself both the routes it takes through the environment, so how it controls its motion, but also the locations it visits in what order. Okay, so now it's reaching the workshop after a bit of an argy-bargy around Michał's desk. So it's visited the workshop, and after the workshop, it will go on and attempt to get to the office door. And this really is kind of key technology for kind of future remote inspection. It's not enough to have a robot platform. You have to integrate it into a larger set of tools, where those tools might be digital twins, remote operation, teleoperation, and sensing. What we don't see on this interface is anything to do with sensor processing, where we just get the camera view. But we are able to task it, and that's really one of the interesting things we see here. So the robot's navigated safely around this environment, and it's heading up to the office door, which is the large door you can see up there. So this is an autonomous system. Again, if you jump back to Mihal's camera, you can see the jackal pottering off towards the door up there. And that pretty much wraps up what I wanted to show you. I'm a little bit over time already, but I'm hoping we've got time for some questions. I will keep controlling the robot in the background. If you want to stick some questions in the chat, then that would be great. Unless Helen tells me I have to stop.
Yeah, well, I'm fine to continue for a few more minutes, but I imagine lots of people have other Zoom meetings to be on as it's life now. So yeah, there's time for a couple of questions if anyone has any. Otherwise, thank you all for joining us today. And Morris says send it to the blue zone.
Okay. So the blue zone has been significantly reorganized since the map was built. So the navigation to the blue zone may be a little bit unreliable, but let's see. So questions. Here we go. You can see also the blue zone is now marked as the target for the robot. So we're safely moving there.
Did anything come from the contact with Harwell?
Not to this point. So we're still looking for opportunities to get in there. I mean, in general, I guess particularly as this is potentially a public call, it's probably best not to discuss individual relationships, but we are absolutely looking for opportunities to take this technology into new environments. So if you're watching this and you are at Harwell or you're at somewhere else and you're interested in giving us opportunities to try our inspection robots in your facility, please do get in touch. The work you can see here is really very portable to different robot platforms and different environments. I do want you to kind of, in general, think about the picture I showed previously with those little purple arrows pointing at barrels. And our aim will be to then replicate that on a map like this, such the robot will be visiting individual barrels to take inspections over time. Okay, we made it to the blue zone.
Okay, I don't think there's any more questions, but you've got praise from both Barry and John, so I'm sure that's made your week.
Well, I thank you, folks. I mean, it's as John said, it's a collaborative effort. So colleagues at Manchester, at Lancaster, at Bristol, and at Oxford have all had a huge part in this. So thank you to everyone within the RAIN project for supporting this. So if there are no more questions, I'm going to send the robot one more time to the office door, and we'll take that one off, and then close there. Yeah, brilliant. Yes. Thanks a lot, Nick. I think yeah, we'll leave it there and let people get off. Thanks everyone for joining us. We've got our HRI workshop next week, so do join us if you're interested in that. And then there'll be a slight break in the webinars, but we will continue these even though people are moving back into labs and things, but we're just getting everything coordinated with people moving back to being able to do their lab work as well. So thanks again for joining us, and we will see you soon. Yeah, and of course if you've got other questions for me, please just drop me an email. Always happy to talk and take this stuff forward.